Alright gang, here we go. This is Chem 2, Unit 2. We're starting Chapter 6 here. The next several videos is all going to be centered around Chapter 6 of our textbook. We're going to be talking about electrons, the nature of electrons, how they're both waves and particles. We're going to talk about electron, where they exist around the atom in different theories that have kind of come up. We'll talk about Bohr, then we'll talk about atomic atomic orbitals. We'll talk about electron configuration. Should be fun several videos. All right. So electronic structure. Okay. It's just pretty much about electrons. Like when you hear electronic in chemistry, a lot of people, you should think electrons, not about like electronic components, like the circuit boards and the like, electrons. All right. So when we start out talking about this stuff, we're going to be talking about waves. Okay. Now, the reason we do this is because everything has wave and matter properties. But the smaller you are, the more wave-like the behavior becomes. Okay, so since we're talking about extremely small particles, protons, neutrons, specifically electrons, are extremely small, then they have a lot of wave-like characteristics. So we're going to just briefly recap waves. Some of you probably learned about some of this in physics. We talked about some of this in Chem 1. You've probably learned about it in 8th grade science, so on and so forth. All right, so waves. So here's just like a roughly waves, like in the ocean. Okay, just some terminology we should be familiar with. Wavelength is when we go from one point to another, and it's literally just the length. How long is that wave? Okay, so here they've measured it from crest to crest. All right, or from peak to peak. You could measure the wavelength from the trough to the trough. Just 82 places that encapsulate one complete wave. That would be the wavelength. All right. Let's see. And then also, so frequency is defined as the number of complete waves passing through a given point per second. So like say we'd say, all right, so we've got this wave, we're going to pick this spot right here, and then as the waves go through, we'll count how many waves go through in 1 second. All right, sometimes it's easier to do like 10 seconds, count how many waves you go through and just divide by 10. But anyway, so that's the frequency. All right, so wavelength and frequency are the two most important characteristics that we measure about waves. Okay, they're really useful in doing a lot of math, calculating their energy, and so on and so forth. All right, so electromagnetic radiation, all right, is in essence what we call visible light is electromagnetic radiation. So is X-rays, gamma rays, stuff like that. Radio waves, those are all electromagnetic radiation, and they move as waves through space and other objects at the speed of light. So all electromagnetic radiation travels at the speed of light, which we roughly define as 3.0 times 10 to the 8th meters per second. Right? But as we change, there's different aspects of it. We'll look at a graph here. We can have varying amounts of wavelength and then varying amounts of frequency to correspond, but we'll always be traveling at 3.0 times 10 to the 8th meters per second. All right, it's a constant value. All right, so the frequency is the number of waves passing through a given point. All right, so in essence, because everything has to travel the same speed, they all have 3 times 10 to the 8th meters per second. When we extend the wavelength, the frequency needs to get smaller. Okay, or as the frequency increases, our wavelengths need to get smaller. Okay, and so they have this inverse relationship. So that's very important. I want you to understand that the wavelength. So wavelength is a lambda, and frequency, that's a nu. Okay, are inverse. Okay, relationship. So as wavelength increases, the frequency has to decrease, and then vice versa. All right. Okay. Here's the electromagnetic radiation spectrum. Okay, so notice how our wavelengths appear. We start with very small wavelengths, 10 to the minus 11th, and as we go, they are getting bigger and bigger. So notice that on the high end of the radio frequency, so this is like AM radio would be up here. Some of these waves are up to an entire kilometer long. Pretty bizarre, right? That's really why AM radio waves can travel so far. If you're out in the middle of nowhere, a lot of times your FM radio stations will be all static, but you can still get AM radio station because their wavelengths are so darn long. Okay, and notice that down here we've got the frequencies, and they have the opposite trend. They start small on this end, 10 to the fourth, so that means there's 10,000 waves per second, right? 10,000 waves per second, so that'd be 1 with 4 zeros. And then as you go this way, when you hit very, very small wavelengths, you have very, very high frequencies, okay? So 10 to the 20th, so that'd be 1 with 20 zeros, okay? Yeah, my brain's not putting together that right now. But anyway, so that's a really, really high frequency for a very small wavelength. So notice we've got this inverse relationship. Okay, visible spectrum is here, so our eyes can detect wavelengths between 400 and 750 nanometers. All right, so one thing I don't like about this graph is that it puts it makes it look like these are frequencies, but these are in fact the wavelengths. Okay, and because we already determined that the speed of light, we already said that the speed of light is always constant, 3.00 times 10 to the 8th meters per second, then this is the relationship they have. So the two multiplied together always have to equal 3.00 times 10 to the 8th. So if our wavelength gets bigger and bigger, that means our frequency has to get smaller and smaller, and vice versa. All right. Here's just some examples of electromagnetic radiation. Okay. So, and kind of like their general symbols. So like ultraviolet and visible are around in the nanometer space, right? And radio waves are in the kilometer space. Television, like your television. Well, nobody really has TV antennas anymore. Some people do, but for the most part, they're dead. But anyway, those waves are about a meter long. Okay, so that's why you had those big bunny ears. I'm sure you guys have all seen bunny ear TVs, right? They're like a meter long, and they stick up real high off the top of your TV. Okay. So waves, nice and dandy, right? It explains how our electrons can travel through things. It tells us how it can travel through space, and so on and so forth. It lets us predict their speed and their wavelength, their frequency. Lots of different properties of electrons are described by the fact that they have wave-like characteristics. However, there's three main things that scientists discovered that point to the fact that electrons aren't purely waves. Okay, and these are the three that we're going to talk about: the blackbody radiation, okay, blackbody radiation, the photoelectric effect, and emission spectra. All right. So blackbody radiation, okay, is the idea that you could take, like here they've got this looks like an acetylene torch. Okay, and they took like an iron nail and they made it glow. Now you can imagine if they turned off the torch, what would the nail do? Well, it would continue to glow for a while until it cooled down, and then it would stop. So this is called blackbody radiation. It's the fact that we no longer, if we take this heat source away or this energy source away, this iron thing still continues to give off energy. That's not really explained very well by or by the wave nature of electrons. We have to look at particle behavior in order to explain that. Okay, so this guy named Planck came along, and he had this idea that that instead of energy just being like this continuous thing, that you could just have infinitely incremental amounts of energy and just grow from there, that your energy always comes in what are called quanta or quantum. Okay, so you've probably heard of quantum mechanics. Okay, quantum mechanics is really the idea of having individual packets of energy and the mechanics involved, or like how the electrons function in light, so on and so forth, at those individual levels. Okay, so this is a kind of a good way to kind of understand what's going on. So you've got a guy walking up a ramp. Now that ramp, you could take infinitely small steps, and you would make your way up the ramp, right? Eventually, right? If you took infinitely, it'd take longer and longer, but you could make it just by like adding just a little bit at the time. But if you're going up the stairs and you take infinitely small steps, you'd be stuck on the same step forever, right? Because until you put enough energy in to lift your foot up that gap right there, you are never going to make it up that next step. Okay, so this is like the quintessential example of being quantized. Okay, so in order to make it up a stairs, you have to raise your foot up that 6 to 8 inches. Okay, if you don't lift your foot up that high, you're never going to make it up the stairs. But on a ramp, you can do it infinitely small. Okay, so that's kind of the quintessential idea of quantized energy. That as we give energy to things and take energy away, it always has to come in a specific sized packet. All right. So that kind of helped explain blackbody radiation. Okay, now the photoelectric effect was the next thing that kind of was interesting to think about. All right, so Einstein used Planck's idea about the quantized energy to explain the photoelectric effect. All right, so this is kind of essentially the same thing. We've got photons that are hitting the surface of some metal object, and then the electrons being emitted from that object are coming off, and they're coming at a different energy than the way they hit. Okay, so and depending on what the metal was, they would emit energy at different levels, the different electron levels, and so. And then if you didn't shoot enough at it, then it wouldn't do anything at all. Okay, so like you had, imagine your iron nail. If all you do is hold it under, your light bulb in your room, it's getting energy from that light bulb, right? And electromagnetic radiation is coming off your light bulb, hitting that nail, but the nail isn't starting to glow like it did when it had the energy from the acetylene torch in that previous picture. Okay, so it takes a certain amount of energy to start making iron in your nail start to glow with that blackbody radiation or that photoelectric effect. And so all different metals kind of have different levels of energy they need. Okay, and so based on this kind of idea, and we're kind of blowing through a lot of this because we don't really need to get in the nitty gritty of this. Take physical chemistry if you really find this stuff fascinating. All right. And so Einstein and Planck together kind of concluded that energy is proportional to the frequency, and by a value called Planck's constant, which is the 6.626 times 10 to the minus 34th. So you can find the energy that's emitted by simply taking Planck's constant times whatever the frequency is of the energy that hit it. So we've got if we can find the frequency of this, we can find the energy that comes off of here. All right, so that's the photoelectric effect. And finally, we have atomic emissions. Now, this is kind of interesting, and I find it absolutely fascinating how stuff like this was kind of discovered. Okay, so the idea is we take these glass tubes, and we did this in class. Okay, and we take these glass tubes, and we put an anode on one side, a cathode on the other, essentially just two metal chunks. But inside, except for those metal chunks, it's just got elemental gas of just whatever it is that gas is. Okay, that's it. Okay, and so all right, number one, who's just putting that gas in a tube just by itself? Okay, so that by itself is a little weird for me. But then somebody else is like, well, look, I can put it in this tube, and somebody's like, ooh, we could run electricity through it. And so anyway, so then they take it and they stick it in a little container, and so so the ones we have at the school look kind of like this. And so they've got it's got a power cord that comes off here like this, and then you can stick these spectrum tubes, the atomic emission tubes, in here like this, and then they look like this and they glow, right? And they've got a little switch to the side and they make an awesome hum. They go or whatever. Okay, anyway, so they notice that depending on what gas we put in, we get different lights. Well, that's kind of exciting. Neon is kind of a red color, and hydrogen's kind of a purple color, and so you get all different sorts of ones. Okay. But then they noticed that as we did this, you could actually take a prism or diffraction gradient and turn it, and you could see that these guys would split up into specific wavelengths of light at different colors, and each one would have different amounts of lines, and they'd be different colors. And each individual element that they stuck in these tubes and ran electricity through had a very specific, almost as if it was a fingerprint. So you could actually identify what the gas was that was in your tube purely by running electricity through it and measuring the distance between the lines. Okay, and you could figure out the wavelengths and so on and so forth. Pretty cool idea. All right, so this video on the PowerPoint you can see on Classroom is pretty good. It shows you 5 or 6 different ones, and we also looked at them in class. All right, so for atoms and molecules, okay, we didn't observe what's called a continuous spectrum. So if you imagine a picture in your mind's eye, a rainbow. We've all seen rainbows, right? So you see a rainbow, and you know that the rainbow is just kind of one color stream, and it follows just Roy G. Biv, right? The red bleeds into the orange, which bleeds into the yellow, which bleeds into the blue, etc., etc. Okay. or the green into the blue, except sorry. And then so we get what's called a continuous spectrum. So here's just like a flashlight shining through a prism, and we get this rainbow. And notice how these colors just kind of bleed one into another, and they're kind of, you know, hard to, there's no distinction between the two. Like, sure, you see red, but it's hard to say that when that red turned to orange. Like, you know, so it's all blurred together. Now, if we take our elements from before, these guys here, and we hold up the diffraction gradient, essentially a prism, and we look at it, we'll see very distinct lines. So for hydrogen, we get 4 distinct lines. Okay, and they happen to be at these values. Okay, so you get like a 400, you know, 10, 20, 30, 40, 50, yeah, 410 nanometer purple line, and a 435 nanometer like indigo line or lavender line, you know, so on and so forth. And then for neon, you get, you know, a plethora of lines. You get all sorts of lines here. And so each element kind of has its own unique line spectrum. Now, if you do it in a purely dark room with a diffraction gradient with very precise measurements, you can get these lines very specifically. When we did it in class, remember, we had some ambient light going in from the windows and just kind of off of our phones, and just kind of, it's really, really hard to get a perfectly black room in the classroom. So you did see some blurriness. You know, you could see some of the other colors behind it, and that's purely just ambient light just kind of shining from everywhere. But if we were in a perfectly black room, we could have seen these perfectly just like this. Okay, so scientists thought this was super fascinating, right? Like, this idea is like, oh, what the heck? We can take this thing, and then these electrons only give off these wavelengths, right? So hydrogen, like here we've got this mixture of like a purple with lavender, a teal, and a red, and when you put those colors together, you get this purple, like light purple looking, you know, color tube right here. Okay, and the neon is something like that. So look at neon's pretty orangey. So notice how we've got these colors down here kind of outweigh, and so that's the color it makes up, is made up of kind of our eyes just seeing all those colors at once, right? So scientists thought this was really fascinating. It's like, well, why the heck would the electrons that are coming off, like, they understood they're coming off as waves and our eyes are interpreting them as waves, but why are they doing it only at specific levels? Well, this guy named Balmer came along, and he discovered a simple formula. And we're not going to look at the formula, but it's pretty simple, and it just looked at hydrogen and it allowed you to correlate those 4 wavelengths, and you could just kind of break them up for hydrogen. And then Rydberg came along and said, hey, that formula is pretty nifty. I'm going to make this a little bit better. Okay, so he came out with, or he changed Balmer's formula, and he came out with this formula that related the inverse wavelength to the energy levels of those two things, and it used what's called the Rydberg constant to relate those two integer levels. Now, the Rydberg constant is this RH value. Okay, and I think this is pretty funny. Like, for a long time, I thought somebody was trying to play in a trick on Rydberg, and was like, yeah, we're going to put an H on his constant, so he thinks that, so everybody's going to spell his name wrong. Like, and me personally, I spelled his name RHYDBERG or RYDBERGH for a long time. Like, it's like, where the heck does this H go, right? But then I realized, oh, the H is because it's for hydrogen, right? And so, anyway, those kind of things dawn on you, like, even after years and years of doing this stuff. Okay, and then, so he came up with this formula. We won't really do anything with it, but it is pretty simple to use. Okay, and then Niels Bohr explained why this mathematical relationship worked. Okay, so Niels Bohr came along and came up with this idea here, and he came up with what's called the Bohr model of the atom. And essentially, the Bohr model is stating that you've got the nucleus, right, that's sitting right there, and then you've got energy levels, and now you get to see my awesome artistic abilities, all right? Oh my goodness, so these circles should be getting closer together and closer together. So you got your nucleus in the middle right here, okay? Nucleus right there. And then you've got energy levels at 1, 2, 3, 4. And as you go up, these energy levels get closer and closer together. And so these electrons, he supposed, were orbiting the nucleus, almost like planets around the sun. Now, the planets around the sun orbit elliptically, right? They're kind of funky shaped, almost like egg-shaped orbital paths. But these these electrons are orbiting them in a circular path. So you got n equals 1. Okay, so this would be what's called the ground state. So this is where electrons want to live. And then it can jump up to n equals 2. Now notice that these kind of look like the steps. Remember how the guy walking up the steps, he had to like put in a certain amount of energy with each step as he goes up. If he didn't have enough energy, he would not move up to the next step. All right. So this kind of idea, Bohr took that quantized energy model and threw that in together with this idea of the atomic emission spectrum for hydrogen. And so he said, all right, we have an electron that's sitting here at n equals 1 on this ground state. If we want to move it up to n equals 2, we have to give it a certain amount of energy. Okay, and it kind of depends on what that energy is, depending on what your two n levels you're starting on. All right, so he defined the bottom level of wherever that electron was ground state, and then the next one was the excited state. All right, and you could jump up to any level as long as you provided enough energy. Then, once you gave it that much energy, that electron could fall back down into another energy level, but when it did that, it would always give off that amount of energy back again. So it started off at n equals 1, moved to n equals 2, absorbed that specific amount of energy it takes to move from 1 to 2, and then when it fell back from 2 to 1, it would emit that energy back again. All right, so that's kind of that was the general idea of the Bohr model. And so when we see these atomic emission lines for hydrogen, they were directly related to the wavelength of the light that was given off or absorbed when those electrons were jumping up and down between energy levels. Okay, so the electrons can be at any of these energy levels. You just have to give it that much energy. Okay, and then we can calculate the energy it needs by using this formula, E equals h nu. All right, so that's the Bohr model. Okay, and we kind of talked about this. Just kind of jot this down in your notes. And so he took, so it is kind of this culmination of everything that happened before. So he took the Rydberg constant, he took the Planck model, Einstein's ideas, threw it all together, and came up with this thing for the Bohr model. All right. Okay, and so these values of the transitions are the energy levels. So I kind of blew through all of this just a second ago, so just pause the video and take notes. All right, now this is our last slide for this video. All right, and so I just want to point out now the Bohr model is really, really awesome, but only in the specific case for hydrogen. All right, it only works for hydrogen. Once you move past hydrogen, electrons start acting different because there's going to be more than one electron. When there's only one electron with hydrogen, the Bohr model is like perfect, if like no problems whatsoever. Okay. Now, but with the Bohr model, but once we move past that, things start falling apart, and that's what we're going to move on to in the next couple of videos. Okay, so what we end up finding out is that the electrons, like based on the Bohr model, if you had more than one, they should be repelled by the electrons or absorbed into the nucleus, right? Because positive and negatives attract. Okay, so what happens is that this circular motion of these atoms that are orbiting the nucleus cannot possibly be purely wave-like. They have to have some particle nature in them as well. And so that's where we're going to lead off for this video. All right, I'll see you on the next one where we talk about orbitals.